Hi everyone, today we are going to learn about a new congruence shortcut. Up till now you have learned about 4 of them that work. We have 4 congruence shortcuts that work. We have SSS, SAS, ASA, and AAS. We have 4 congruence shortcuts that work, and we're going to learn about a new one today. But first, we're going to look back at why SSA did not work, why it's not a congruence shortcut. So here's an image that shows you why the SSA doesn't work. In this image, we can see that for these 2 triangles, they both have this congruent angle at angle A, they both have side length AB, and they both have the side length BC. Here it's called BD, but it's the same side length. And there's 2 different triangles. They're definitely not congruent. So here is an example of why SSA doesn't work. So we can see that 2 triangles can be drawn using the given angle and the 2 given side lengths. Therefore, SSA cannot be used to determine the congruence of 2 triangles. So that was just going back and showing you why SSA does not work. But what happens if the given angle that we have is specifically a right angle? Let's look at that demo that we did the other day and see what happens. Okay, so here is the demo that we did the other day that shows us why the SSA shortcut doesn't work. Just to remind you what we saw, this is showing us that there's 2 triangles that have the same measurement, that both have a length of 8 here along the side, that both have a 30-degree angle right here, and both of these triangles have a length of 6. On the triangle on the left, so this small one, that length of 6 is right there, and then for the really big triangle, the length of 6 is right here. So we're seeing 2 different triangles that have those same things, the length of 8, length of 6, and the 30-degree angle, and so therefore side-side angle is not a congruent shortcut. Okay, so now we want to see what happens if this triangle is specifically a right triangle, if there's a right angle in there. So I am going to change the length of this side, the one that's swinging, and we're going to look at what happens as the triangle on the left, the one that's shaded in, becomes closer and closer to a right triangle. Okay, so as this length changes, as I change this, and I can make it different lengths, you can still see the 2 triangles that are being formed, the one on the left and then the big one on the outside. But if I start going here, well, one, if I get too small, it doesn't even make a triangle, right? So that's not going to work. But let me go back to where I was. So if I go a little slower as I'm getting smaller and smaller, and you can see how it's starting, oh, and there it is, it became a right triangle. So now that it became a right triangle and we have this right angle right here, it's only making one triangle. We only have one triangle with all these different dimensions, with the 2 sides and the given angle. We have one triangle. We're only seeing one distinct triangle, not 2 like we were before. So remember, the reason why SSA wasn't working is because we could make 2 triangles out of those different dimensions. But here we're seeing one distinct triangle, specifically when we have a right triangle. Okay, so what is the conclusion? In that demo we just saw, we saw that only one triangle can be drawn using the given angle when it's 90 degrees and the 2 given side lengths. Therefore, SSA can be used as a shortcut to determine the congruence of 2 triangles, but only when it is a right triangle. It's a very specific situation. So since it only works for right triangles, we're going to give it a special name, and we're going to call this shortcut HL, because the 2 sides are specifically a hypotenuse. I'm never going to fit that in this little spot here. Hypotenuse and a leg, in addition, of course, to the right angle. So when we talk about having SSA, one of the sides is the hypotenuse, one of the sides is a leg. The angle is specifically a 90-degree or right angle. And so it's a very specific case. So instead of calling it SSA for right angles or right triangles, we're giving it a new name called HL because we know it has to work for right triangles only. So we're still not using the SSA acronym. SSA still doesn't work. It only works when it's specifically a right triangle. So now we're going to call it HL. So when you make your list of shortcuts that work, we now have SSS, SAS, ASA, AAS, and HL. So there's actually 5 shortcuts now. Okay, so what does this really mean? How is it going to affect what you're doing? Before today, if you had this picture right here, and you can see I've got 2 congruent sides, right? I've got this one here that's congruent to that one over there. I've got this one here congruent to that one there. I have 2 congruent sides, and then I have a congruent angle. I have these right angles here. Before today, you would have just said, no, I can't do this. I can't prove them congruent. We don't have enough information. But now, specifically because the angle that's shown there is a right angle, even though it really is SSA, but because it's a right angle or a right triangle, now we're going to say, well, yes, they are congruent by HL, because we know we can't use that one. So before today, we would have said no, but now with the new information, these are congruent by HL, by hypotenuse leg congruence shortcut. They have 1 pair of congruent hypotenuses, 1 pair of congruent legs, and they have right angles inside the triangles. Okay, so when you're writing a proof involving, that's going to use the HL shortcut, in the proof, you need to show 3 things. The first thing you have to show is that you do have right triangles. Notice that it says right triangles and not right angles, and I'll show you how that works in the proof here in this example. You have to show that the hypotenuses are congruent, and you have to show that 1 pair of legs is congruent. So you're showing that I have right triangles, and then I have the 2 pairs of congruent sides, which are specifically hypotenuses and legs. Here's an example of what an HL proof will look like. Let's say we have this picture, ABCD is a rectangle. We want to use this information to prove that triangle ABD is congruent to CDB. So it's already done for you, but let's walk through this. Step 1, statement 1, ABCD is a rectangle. That's given. Statement 2, angle A and C are right angles. Well, how do we know that? Well, if a quadrilateral is a rectangle, then its angles are right angles. So that's just a thing we know about a rectangle. That's a fact about a rectangle. Statement 3, triangle ABD and triangle CDB are right triangles. If a triangle contains a right angle, then it's a right triangle. This is a step that we haven't used before. We haven't needed it. So make sure you think about this step and like how you would use it again in the future. If you're trying to use HL, something like this needs to be in your proof. You want to state you have right triangles, and the reason is if it has a right angle, then it has a right triangle. Obviously, in order to be able to use this step, you need to have somewhere earlier that you have right angles. You can't just say you have right triangles if you don't have right angles. Okay, then step 4, BD is congruent to itself. Remember, that's just a reflexive property. That's how we're getting this right there. Actually, let me go back and mark what I had before. The fact that angle A and C are right angles. And then we have the congruent hypotenuses. And then step 5, AB is congruent to CD. If a quadrilateral is a rectangle, then its opposite sides are congruent. That's a fact about a rectangle. And then finally, we get to our congruent statement. Triangle ABD is congruent to triangle CDB by the HL congruence theorem. You don't have to write congruence theorem. You can just say HL. That's enough. Now, I didn't say this earlier, but notice what I have here in the bold part. I just like to list the 3 parts to make sure I'm kind of like checking it off for myself. If you don't do that, it's not wrong at all. That's not required, but I think it's really helpful. Just like how I showed you in the other proofs, I like to show, whether I have side, 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 or side angle, side, so I can see my pieces. I'd like to show here, okay, kind of to myself, I've got right triangles, I've got congruent hypotenuses, and I've got congruent legs. You could even just, instead of writing all that out, you could even just write an H next to that step and an L, just to help you out if that's useful to you. Okay, now we're going to do a proof from start to finish, and we'll do this one together. So we have our diagram. Given is that CD is congruent to EA. Let's go ahead and mark that. AD is the perpendicular bisector of CE. Think about what that means. If it's perpendicular to it, it's forming a right angle. If it's a bisector, it's cutting it in half. So there's 2 things we're getting from that. Let's go ahead and mark that. So again, it's AD is the perpendicular bisector of CE. So AD is forming a right angle with CE. So we can put those right angle marks in there. And it's bisecting CE. So we're going to mark that those are congruent. So I'm going to put that this is congruent to that. Notice that they're not perpendicular bisectors of each other. So it's not bisecting AD, but we're bisecting CE. Make sure you understand that difference. Okay, so now we're going to write a 2-column proof to show that these two triangles are congruent. Let's go ahead and set up our table. And let's get started with what we're given. So we know that CD is congruent to EA, and that is given. And we know that AD is the perpendicular bisector of CE. And that is given. Okay. Then we look at what other information that we got from those given statements, and from step 2, from the fact that it was a perpendicular bisector, we got a couple different things. We first, because of the word bisector, we knew that CB and EB were congruent. We marked them, but now we can go ahead and state that. So we can say that EB is congruent to CB, and that is from definition of bisector, or just bisect, you could say as well. And then the other part from that was that angle CBD and angle EBA are right angles. And that is from the definition of perpendicular. Okay, so I forgot to mark these things back here, but when we did CD was congruent to EA, that is our hypotenuses. And when we said that EB was congruent to CB, that is our legs. What we still don't have in order to use the HL shortcut is that we need to state that we do have right triangles. So we need to have a step 5, that triangle ABE and triangle DBC are right triangles. And that's just definition of a right triangle. All right, now finally, we can state in step 6 that triangle CBD is congruent to triangle EBA, and our reason is HL. So remember, we're not going to say SSA, even though it's using the SSA shortcut, but specifically for a right triangle, so the shortcut is just HL.